Welcome back to Calculus 2. This will be a continuation of our lecture on power series representations of functions. We're just going to pick up right where we left off from part 1 and continue. All right, so to briefly review part 1, we looked at how we can take our geometric series and its power series representation and basically perform algebraic manipulations to make our function kind of resemble that. We rewrite it in the form 1 over 1 minus something, and then we make a replacement. The functions for which that is applicable are very limited. They have to generally be rational expressions, fractions, or some combination of them with basic multiplication. What we're going to start to look at for this second part is how we can use the tools of calculus to expand the types of functions that we can represent as power series. And this will give you some insight into the utility of power series as you might see them in a advanced science course or advanced engineering course. All right, so the starting place for part 2 is, let's think of a basic power series there. We'll, for simplicity of just writing out, we'll go with the version centered at 0. So we have a term with power only x rather than x minus a. And we get a set of terms there. We have a few of them written out. We have a constant term, x to the first power, our linear term. We have an x squared, a quadratic term, x cubed, a cubic term, so on and so on. Now, the advantage of using power series is it's very simple to do all sorts of operations with powers of x. Very simple to add like terms, simple to divide, and even very simple to perform the basic operations of calculus, differentiation and integration. So just to state it, we have what might have been addressed in your Calc 1 course as the power rule, the derivative of x to the n. Bring the exponent down and then subtract 1 to get the derivative of x to the n as n times x to the n minus 1. There's an equivalent and related version for the power rule for antiderivatives. Here, there's an exception. This doesn't apply when the exponent is -1. In other words, the antiderivative for x to the -1, rewrite that as the antiderivative of 1 over x. You know that it's natural log of x. So as long as the exponent is not -1, we have this power rule for antiderivatives. You add 1 to the exponent and then divide by that new exponent, n plus 1. Of course, there's some complications with reversing differentiation. Here with antiderivatives, the complications are you basically get an infinite amount of antiderivatives accounted for with the plus c. All right, now we're going to basically combine these ideas with power series, and instead of maybe rewriting our function algebraically to look like 1 over 1 minus something, now the something that we'll be doing, the rewriting, would be some ideas of calculus, integrating or differentiating our function to make it resemble one of our previously known power series representations. All right, so the first thing we're going to get to in this second part is this theorem. There's not an official name for it, but I encountered it in my mathematics and then physics courses, known as term-by-term differentiation and term-by-term integration. What this title is alluding to is a very simple way to manipulate power series. Since our power series is an infinite polynomial, kind of a sum of an infinite amount of powers of x, we can calculate derivatives just by differentiating each term. We can calculate antiderivatives by integrating each term of that power series. Now, that is just the basic or intuitive idea of what this theorem, the term-by-term differentiation and integration theorem. Of course, there's some technicalities that we need to be aware of for mathematics, since we are in a mathematics course. Usually those technicalities and details are kind of swept under the rug and not talked about too much in your higher level science and engineering courses, but they are important. So if we get into the precise statement of the theorem here, it basically starts with a power series representation that has a known interval of convergence, and we're writing it in absolute value notation as absolute value of x minus a is less than r, where r, we refer to that as the radius of convergence. All right. The other part of what this theorem supposes is that we have a function, f of x, that we are defining to be this power series. So in other words, f of x, we're representing it as a power series. All right, what this theorem basically says is if we have our function f of x represented as a power series, then we can get power series representations for the two main calculus operations on a function: differentiating a function and integrating a function. So with our power series representation for f of x, we can define the derivative and its power series representation basically by applying the power rule. Notice how it fits the basic power rule from Calc 1 above. We're going to be differentiating x minus a to the nth power, and we would bring the power down. That gives us the factor of n in the first result for the power series of f prime. And then we subtract 1 from the exponent, going from x minus a to the nth power to the derivative containing x minus a to the n minus 1th power. Now be careful, that is not all we apply to differentiate that. Technically, we would want to use the chain rule, since we have kind of a function raised to a power, a function inside a function, but the derivative of the inside, the derivative of x minus a, is just 1. So we don't get any extra factors there from the chain rule, but we get this result by applying the basic power rule for derivatives. Now, one thing I want to point out for that first result is notice our function f of x has the starting index in its power series as n equals 0. The derivative has the starting index at 1. That's not a mistake. Write out terms to convince yourself that that is correct. We have this version stated with the index starting at 1, so that way we see going from the function, which contains x minus a to the nth power, this derivative version for the power series has basically the term n times x minus a to the n minus 1th power coming from the power rule for derivatives. In order for that to work, to fit that form, we have to start the index here with 1. All right, the other part right after the comma there is what this basically says in notation, but not outright stating it, is if our function has an interval of convergence of x minus a in absolute value less than r, then the derivative power series representation has the same, at least radius of convergence. Looks like the same interval of convergence, but remember, for the interval of convergence, we have to check the endpoints if we can include either one of them. The endpoints being the left endpoint, little a minus capital R, and the right endpoint being little a plus capital R. So the result says if your function and its power series representation has a certain radius of convergence, then your derivative power series representation has the same radius of convergence. The second result says something similar, but instead of differentiating the function f of x, we integrate. And notice on that right-hand side, the first thing we're including is the integration constant, the always forgotten plus c. And then we have the term-by-term integrated power series. Now we integrate x minus a to the nth power and apply the power rule for antiderivatives. That's where the n plus 1 in the denominator comes from. And like the first result, the antiderivative of f of x and its power series representation has the same radius of convergence, capital R. Okay, let's go ahead and jump straight to an example. We're going to take as our starting place a known power series representation coming from the geometric series. 1 divided by 1 minus x equals the power series involving the term x to the n, where the summation goes from n equals 0 to infinity. Now, what I'd like you to do is make an attempt at this. You have to get a little creative now. We're no longer relying on algebraically manipulating our function to fit the form 1 over 1 minus something. For these examples, after our term-by-term differentiation or integration theorem, we're going to want to try to differentiate or integrate 1 divided by 1 minus something. And then we're going to try to think, how can we connect our function and see how it's related to 1 over 1 minus x. Might be an algebraic manipulation, might require derivatives, might require antiderivatives, or maybe a combination. Pause the video and give yourself an attempt at this. We'll check in a few minutes. All right, welcome back. If you feel like you were stuck with this one, that is okay. It starts to get a little bit more complicated since it's not quite as straightforward or obvious what you would want to do to 1 over 1 minus x to get the given function, which is here, 1 divided by 1 minus x quantity squared. All right, now one operation that you could do is take 1 over 1 minus x and square both sides of that. Now, while you can do that, it's very difficult to work with that power series, all infinite amount of terms squared. You can talk about, like we did, adding or subtracting power series. You can define multiplication and division of power series. We're going to save that a little bit later in the course when we get to Taylor and Maclaurin series. It'll be a little bit easier to address the why you would want to multiply or divide power series. So we could square each side of this result, but that's going to lead to a very complicated squaring of the infinite sum. Most students complain when you have to FOIL 2 or 3 terms. Here you'd be FOILing, squaring an infinite amount of terms. So let's not do that. Let's try to think of how we can take our function 1 over 1 minus x and perform some calculus manipulations. All right, and the first one, this is a good one to start with. It might not be as kind of unclear where this is coming from, but we're going to take our function 1 over 1 minus x and calculate the derivative. All right, and if you do that, you might be tempted to differentiate 1 over 1 minus x by using the quotient rule, which you can. But here, I think it's more efficient to rewrite 1 divided by 1 minus x, to rewrite that as 1 minus x, that quantity raised to the negative first power. There's a quantity in the denominator. You can rewrite that now as a negative exponent. The advantage of rewriting it like this to calculate the derivative is we don't have to use the quotient rule, but now we can apply the chain rule. We have an inner and then outer function. If you apply the chain rule, you should get that your derivative comes out to be 1 divided by 1 minus x squared. And we were kind of rewriting that from having 1 minus x to the negative second power. We're rewriting that negative second power as a factor of 2 in the denominator. All right, so the connection here from our starting place of the geometric series result is that it is the derivative of 1 over 1 minus x that gives us our function 1 divided by 1 minus x squared. Now, how do we connect this to the previous theorem? Well, what this is telling us is we can basically differentiate our known power series representation, the summation from n equals 0 to infinity of x to the n. And that's going to be very easy to differentiate term by term. So to put this together, we recognize 1 divided by 1 minus x squared as the derivative of 1 divided by 1 minus x. We then, for the part in the brackets, replace 1 over 1 minus x with its power series representation, and then differentiate that power series term by term. And if we do that, the advantage again of using power series, while this is very complicated and new, differentiating an infinite polynomial, differentiating x to the n is very simple. That is one of the advantages of using power series representations for functions. They're very simple to manipulate using the ideas of calculus. If you differentiate x to the n, you get the term n times x to the n minus 1. The only thing that's probably a little confusing here is in order for this summation formula or version to work, where the term is n times x to the n minus 1, we have to start the index no longer at n equals 0, but at n equals 1. And again, in red right below there, you might be able to convince yourself why there's some kind of coefficients that no longer match the exponents. Okay, the other thing that the term-by-term differentiation / integration theorem tells us is our starting power series representation had the interval of convergence, absolute value of x being less than 1. Our power series representation for the derivative, like we're using here, has the same interval of convergence. Absolute value of x less than 1. So here, after basically differentiating our known result, the power series for the geometric series, we make the connection and get our power series for 1 divided by 1 minus x squared. All right, now, just to be clear, the interval of convergence gives you the open interval from -1 to +1. We should check in detail what happens at either endpoint, x equals 1 and x equals -1. If you do that here, plug that into the power series, you'll find that basically the power series diverges at both endpoints. So we can keep both endpoints excluded and have our interval of convergence as the open interval here, values of x strictly between -1 and 1. All right, now this was a simple example where it was kind of rather simple compared to some of the ones we'll be getting to of how to make the connection between 1 divided by 1 minus x and our function, just a simple differentiation here. Now there's a second version, just to tie this into kind of some references you might be looking at. We have it stated here where the term is n times x to the n minus 1. The starting index starts at n equals 1. Now, some textbooks and references prefer to express this only containing x to the n. If you do that, you can convert, replace within the first version, the n equals 1 version for the starting index, make the replacement everywhere, n being replaced with n plus 1. That'll convert the power of x from x to the n minus 1, replace n with n plus 1, n plus 1 minus 1 gives just the exponent n in that second version. So there's kind of two equivalent versions here. Neither one is any more correct or wrong than the other. It's just different labelings with respect to the power and the starting index. And you're likely to see both versions switched back and forth and used kind of what occurs next in science and engineering courses, maybe in what you'll see in your differential equations course, where both versions are used. All right, now with that first example out of the way, let's get to some ones that require kind of a little bit, again, more creativity with how you would make the connection to 1 divided by 1 minus x. Now, if you're, again, feeling adventurous, as we mentioned before, pause the video to make an attempt, but these are kind of a lot more complicated. So we're going to kind of walk through these a little more step by step, leaving you plenty of places to pause the video and try to complete it. So maybe make an attempt to think, how is this function related with derivatives or antiderivatives to 1 over 1 minus x? All right, any ideas? Well, what's going to work for this example is we're going to make the connection, the antiderivative or integral of 1 divided by 1 plus x, that integrates to natural log of 1 plus x, plus c, of course. All right, now you might be saying, wait a second, Professor Anderson, 1 divided by 1 plus x doesn't fit our geometric series result. You're right, but we can just make a replacement from what we saw in part 1. We can just use an algebraic replacement for the part inside the integral. So maybe that gives you a hint. See if you can first find a power series representation for 1 divided by 1 plus x. We'll check in a few seconds. That should be very minimal in terms of the work required. All right, hopefully you were successful with that. That doesn't require too much. It was very similar to one of our first examples we did, 1 divided by 1 plus 2x. We can use our algebraic manipulation tricks here, rewrite the denominator 1 plus x as 1 minus negative x. Okay, we can replace in our geometric series, make the replacement, the part in parentheses, we're going to replace it with negative x. And we basically get our power series where the term is negative 1 to the n times x to the n. We took the nth power there of negative 1 and x since we're multiplying. Okay, how we connect this back to our term-by-term differentiation / integration theorem is we have a power series now for 1 divided by 1 plus x. What we want to do to get our function, natural log of 1 plus x, is integrate that function, 1 divided by 1 plus x. So what we do is integrate the power series for 1 divided by 1 plus x. We're going to integrate that term by term. So notice in the integral there, we're replacing that function, 1 divided by 1 plus x, with its power series that we found above. Now, what essentially we're doing looks very simple. We're basically going to integrate the power of x. So we're going to integrate x to the n. But this is a huge conceptual leap to cover this in complete mathematical detail. Now, just to explain why this gets complicated, the summation here, the infinite series, that involves an infinite process, adding up an infinite amount of terms. Think back how you defined integrals when you first started area beneath a curve and approximating the area. You basically added up an infinite amount of very narrow or infinitesimal rectangles. So integration is itself another infinite process. Very, very, very much later in the kind of mathematics courses, maybe getting close to like Calc 15, Calc 16, you'll kind of see in detail when you can exchange two infinite processes. But we're going to keep it rather simple here and just relate this to our term-by-term differentiation and integration theorem. All right, so all we're doing at the very end there is we're bringing the integral within the summation and then integrating the power of x, integrating x to the n, which only requires the basic power rule for antiderivatives. Add 1 to the exponent, divide by the new exponent. Okay, at this point, we're pretty much done. For this example, we can actually go further and determine the value for the integration constant. Now we have to get creative and think about a value of x within our interval of convergence. Remember, these power series representations are only valid for values of x within the interval of convergence. And here, our interval of convergence is absolute value of x is strictly less than 1. And a nice value in that interval, a nice number between -1 and +1 is 0. So what we can do is in this power series representation, kind of on both sides, we're going to plug in x equals 0. The nice thing about the right-hand side with the powers of x, just think what 0 to any power is. 0. So if we plug x equals 0 into both sides, you end up with natural log of 1 on the left side. Since everyone's experts in their pre-calc course, you remember all things exponentials and logarithms, you all recall natural log of 1 is 0. All right, so what we find here with that equation, we get 0 equals c, so we get c equals 0, and that gives us a completely determined power series representation for natural log of 1 plus x. Now be careful, notice in that last interval of convergence, our basic interval of convergence we found from our geometric series result was absolute value of x less than 1, which is equivalent to saying all values of x strictly between -1 and +1. If you check by plugging in your endpoints, you'll actually find this power series or power series representation, it does converge when x equals 1. You basically have the alternating harmonic series when you plug in x equals 1, and the alternating harmonic series converges. So we can modify our interval of convergence to include the right endpoint, x equals +1. Now, I just want to give a little kind of a brief tangent to how we apply power series. When we started our introduction to infinite series, we briefly alluded to the sum of the alternating harmonic series. We stated it as natural log of 2. We now have the tools to prove or see where that result comes from. Since our interval of convergence includes x equals +1, we can plug that in here and have a conclusive result for a valid power series representation. If we plug x equals +1 in, we have natural log of 1 plus 1, natural log of 2, and then notice on the right-hand side within the power series, you have 1 to the n plus first power. 1 to any exponent or power is 1. And what we find here is an infinite series representation for natural log of 2. We're stating this differently. That power series or infinite series we have there is the alternating harmonic series. We have now found the sum of that. That sum is natural log of 2. Now what we saw here at the very end, this is kind of extra for the problem. That is kind of very much how kind of a lot of known summations or sums for infinite series are arrived at. We start with a power series representation for a function and then plug in an appropriate value for x. It's not the only way you can find sums of infinite series, but it's a rather simple way within the grasp of a student going through Calc 2. All right, let's take a look at our last and final example for applying kind of the term-by-term differentiation and integration theorem. Again, if you're feeling adventurous, give this one a try. This one is probably the most complicated of all. It's probably not obvious how to connect this to 1 over 1 minus something. Check in a few minutes. I'll give a hint to get you started if you're stuck. All right, ready for the hint? We're going to use a result that we probably haven't encountered in a while. Our last time encountering this was probably back in dealing with partial fraction decomposition. And it was something stated first in your Calc 1 course. You first learned that the derivative of inverse tangent is 1 divided by 1 plus x squared. Towards the end of your Calc 1 course, you reverse that to an antiderivative statement. We recognize the antiderivative or integral of 1 divided by 1 plus x squared as inverse tangent, plus c, of course. Now the hint is, can you find a power series representation for 1 divided by 1 plus x squared? I feel pretty confident that you can from the examples that we saw in part 1 of this lecture. So pause the video and make an attempt at this. The rest of the problem is basically finding a power series for the function in the integral and then integrating that power series term by term. We'll check in a few minutes. Hopefully this hint is enough to get you through the rest of it. Welcome back. Let's go through and finish this last example. This one doesn't require too much algebraic manipulation. We basically already have it in the form 1 divided by 1, but here there's a plus, we want a minus. So it's very simple. Rewrite that denominator 1 plus x squared as 1 minus negative x squared. Replace in that denominator of 1 over 1 minus something. The something is now negative x squared, and we get this power series representation. The rest of the problem is recognizing our function, inverse tangent or arctangent of x, as the antiderivative or integral of 1 divided by 1 plus x squared. So we take our power series representation and integrate that term by term. It's a little trickier here. Notice in the power series result or representation for the geometric series, we have negative x squared, and then in parentheses, all raised to the nth power. You have an outer and inner power. You multiply there. So we get as the exponent of x, or base x, 2n. Now, when you integrate that, you apply the power rule there. And if you do that correctly, evaluate that last integral there, the integral of x to the 2n, add 1 to the exponent, and then divide by the new exponent. And we are almost done. We get the power series representation determined up to a constant of integration. Now your trig might be a little murky since you maybe haven't used it as much as you would like. But recall there's some nice values for tangent or inverse tangent, depending on how you look at it. Our interval of convergence from the geometric series kind of works out to be absolute value of x less than 1. And we're going to pick a value of x within that interval of convergence. Let's go ahead and plug in 0. Since tangent of 0 equals 0, that means inverse tangent of 0 is also 0. So if you plug in x equals 0, any value of x would work within the interval of convergence, but we pick a value that we can nicely evaluate inverse tangent at. And that nice value we can evaluate it at is x equals 0. Okay, so we find our constant of integration, again, like the last example, comes out to 0. It doesn't have to. And we get this rather nice power series representation. Notice the interval of convergence includes both endpoints. Check that, plug in x equals 1 and x equals -1. You'll find you get a convergent infinite series in both cases. So we can include both endpoints, 1 and -1. Okay, now that completes the problem, but I feel compelled to give you some insight to what you can do with this. And let's plug in x equals 1 again. That's within our interval of convergence. If you think back to pre-calc, tangent of pi over 4 equals 1. Either think of your special triangles or the unit circle. Now you can switch that around. Instead of saying tangent of pi over 4 radians equals 1, you can rewrite that inversely as inverse tangent of 1 equals pi over 4. If you plug in x equals 1 to that power series representation for inverse tangent, what you get is an incredibly important infinite series. You get an infinite series for pi over 4. Which is alternating. Notice the infinite series there contains 1, minus, plus, minus, and it's basically reciprocals of the odd numbers. And what this puts us on the path to be able to understand is one of kind of many possible ways to calculate pi, which is incredibly important within mathematics and computer science for algorithms on how to efficiently compute pi. Now here, you can manipulate that, solve that for pi, multiply 4 to the other side, and just multiply each term in that infinite series by 4. And the more terms that you add up in that infinite series, the closer that sum will be to pi. If you want a highly accurate kind of value for pi, add up a lot of terms in that infinite series. Now, this is not a good way to compute pi. While this infinite series does converge to pi, it converges very slowly. There are other similar versions that converge much faster and are much more appropriate for computation when thought of with kind of various aspects of algorithms coming from computer science. But that's all beyond the scope of our course. This basically brings us to the end of our first way to find power series representations for functions using calculus along with our geometric series.